Okay, so let's continue section 13.2, line integrals. Uh, line integrals of vector fields. Line integrals of vector fields. Now, what does that mean? Well, all right, let me show you here. So, and we're recording. So you see here in figure 11, you have a particle that starts at a point p sub 0, and it moves in space to a particle p sub n. And it's moving, there's a vector field, okay, acting on the particle. Now it could be acting with the particle to help it move from point p sub 0 to p sub n, or it could be working against the particle, okay? But how are we going to find the work that the vector field or force field does in moving the particle from an initial point p sub 0 to an end point p sub n along that curve C? Well, remember, the way we find work is we take the dot product of a force. Well, if we're interested in the work done in moving a particle in a direction, in a displacement vector, or in a certain direction, a vector in a certain direction, we have to take the dot product of the force acting on, so like pick a point p sub I, okay? Or yeah, like they have there in the picture. So we're interested in okay, what work does the force field do in moving the particle at the point p sub I along the curve? Well, along the curve for a very short distance would be equivalent to that vector, tangent vector t sub I. So if we were to take the dot product of the force vector along with the tangent vector, that would get us the work. But it's only good for a certain distance, a certain little bit of distance, because the tangent vector approximates that curve at the point p sub I just a little bit, just for a very little bit of distance. So we have to scale that dot product by multiplying by some differential. And it could be a differential t, for instance. And if we add up all the little dot products, we will get an expression for the work that the force field does in moving the particle along that curve C. And this is what we're looking at here. So if you have a continuous vector field defined along a smooth curve, then the line integral of the vector field the vector field F now along that curve C is given by the integral of F dot dr. That's a dot product. Okay, and I sort of gave you a quick summary of why this is true. I mean, you're taking the dot product of a vector field F at some point R of t, and you're dot prodding it. You're doing a dot product with a tangent vector, which in this case would be R prime of t, and you're adding up all those dot products, all those little pieces of work together, and that becomes an integral. So that being said, let's go ahead and do an example. Let's do an example here. Okay, let me give you a moment to copy this example down. Okay, so what we want to do is we want to find the work done by the force field, and this force field is given by x squared I minus xy times j. Find the work done by that force field in moving a particle along a quarter circle that starts at 1, 0 and ends at 0, 1. And keep in mind that the work is defined as the integral of f dot dr, but that can be expressed, that's over a curve C, and that can be expressed as, you know, what's the vector field a function of? The vector field changes depending on the position you're at in the field, and the position the particle is at is a function of t. It's a vector function of t, right? Then a space curve, to find the space curve, you have to find the position function, right? That's r of t. You're going to dot that. You're going to dot that with r prime of t dt. Now, why is that true? Well, if you do dr dt, by definition, that just equals r prime of t. Hence, r prime of t dt is equal to dr. R prime of t dt is equal to dr. Okay, are there any questions on that? Okay, well, let's go to the next page. So, okay, what I've done here is I've brought in the figure for this problem. This problem actually goes with example 7 on section 13.2. So what's drawn here is the arrows. The arrows represent the vector field. Okay, and the path here, the path. Okay, and this path, by the way, is, again, this is the particle moving along that space curve in this direction, right? In the counterclockwise direction. All right. Well, the parameterization for that space curve would be cosine of t times I plus sine of tj. Okay, and t would go from 0 to pi over 2. So to compute the work, well, let me ask you this. Based on the picture, does it look like the particle is moving against the force field or with the force field, based on figure 12? Does it look like the particle is moving against the force field or with the force field? That's right, Eric. That's right, Christopher. That's right, Ryan. It's moving against it. So that means when we compute the work should be negative, right? The work should be negative. The work, if the particle is moving along with the force, if the particle moves with the force field, then the force field is helping the particle move from the point, the the point 1, 0 to the point 0, 1. So if the force field is helping the particle move from the beginning point to the end point along that curve, along that path, then the work's positive. But if the force field is acting against the particle, if it's impeding the movement, then we would expect the work done to be negative. And I'll comment that this picture here, this picture, you can draw that picture in MATLAB. I have, under MATLAB programs in Blackboard, a program for section 13.1 that's going to draw this very exact picture for you. Okay, all right. So now what we do is let's find the work. So of course the vector field, right, is x squared I minus x times y times j. So for the coordinates x and y, I'm going to put in the x and y coordinates for r of t. And those are the x and y coordinates for r of t are the cosine and the sine respectively. So x squared becomes cosine squared of t, x is cosine of t, and y is sine of t. Okay. Now the r, the derivative of the vector r of t, is simply negative sine of ti plus cosine of tj. And incidentally, you're able, if you want, instead of using the ij notation, you could use, you know, this notation, right? You could use this notation as well. Are there any questions? Okay, well, we're going to compute our dot product here, and we know how to compute dot products from section 9.3. So the dot product of two vectors is a scalar, and in this case, well, it's a scalar function. And so the scalar function is going to be negative cosine squared of t sine t minus cosine squared of t sine t. But those are like terms, so that just equals negative 2 cosine squared of t sine of t. So now this is really a calculus 1 problem, right? Or a calculus 2 problem, actually. We need to find this integral. So we have integration techniques, integration by parts, substitution, partial fractions. We have a lot of integration techniques. For this integral, what would you suggest we do? What technique's going to work good here? Okay, Ryan, I like that, a u substitution. What should we let u equal to? I agree, the cosine of t. That's right, Ryan. That's right, Rob. Okay, so that being said, may I go to the next page? Are there any questions? Okay. Well, all right. So computing the work, the integral goes from 0 to pi over 2. This here, this is a pi over 2 here, right? And I'm going to let u equal cosine of t. And so, of course, the limits change. The limits change. The cosine of 90 degrees equals 0. And so, we're getting our u limits here, since u is cosine of t. And the cosine of 0 equals 1. All right, and then cosine squared of t just becomes u squared, and the sine of t dt just becomes negative du. And that gets us here. All right, so I'm going to note that a negative times a negative is a positive, and so our work integral now becomes the 2 times the integral from 1 to 0 of u squared du. And u squared, then, u squared, the antiderivative of u squared is u cubed over 3. Limits are from 0 to 1. We plug in the 0, we plug in the 1. And we're going to end up getting negative 2/3 for the work. Okay. And I see here something got chopped off on the bottom. Let me add the word here. Okay. So we end up getting negative 2/3. And we would expect that for the work, because the work is negative because the force field impedes the movement of the particle. We saw that from the picture, that the force field was acting in the direction opposite the particle's movement. Say the force field is like wind vectors, okay? Well, the wind is acting against the movement of the particle. So therefore, we would expect the work to be negative. And once again, in MATLAB, I have a program that will draw that picture for you, that figure 12. That can be helpful. Are there any questions on that? Who's feeling okay, reasonably comfortable with this problem? Ryan's good. John and Robin and Ryan, very good, very good, very good, very good. Okay, well then if there are no questions, I'll stop the recording. I want to say just a few things before our class ends here. But are there any questions? Okay, let me stop the recording.